Welcome back. It's Sunday. I got up 8 a.m. It's 10 a.m. I've been out shopping. Let's read this MOSFET. I was out shopping in Lidl. They had super cheap potatoes. Super cheap potatoes. I'm too sleepy to talk because it's always kind of hot and I'm sleepy and I need a shower this evening and I'm sneezing. Now to buy some cheap grapes, red grapes, like $1.50 now. My camcorder out of focus. Always a lot of cheap potatoes, cheap carrots. I will fry the sausages later and brown gravy. And I did buy more cola for the next week. So let's read this, try to read this. I don't understand much, but I like to read it. Even I don't understand, I like to read it. I need to update my reading list. So I will make a video about it later. In my length now, the camcorder is out of focus, but I cannot do anything about that. So just like to read it, even I not understand much because I'm not that chip designer or electronic engineering. But I just like to read it again. I did read it like 1 year ago.
MOSFET. In electronics, the metal oxide semiconductor field effect transistor, MOSFET, MOSFET, or MOS transistor, is a type of field effect transistor, FET, most commonly fabricated by the controlled oxidation of silicon. It has an insulated gate, the voltage of which determines the conductivity of the device. This ability to change conductivity with the amount of applied voltage can be used for amplifying or switching electronic signals. The term metal insulator semiconductor field effect transistor, MOSFET, is almost synonymous with MOSFET. Another near synonym is insulated gate field effect transistor, IGFET. The main advantage of a MOSFET is that it requires almost no input current to control the load current, when compared to bipolar junction transistors, BJTs. In an enhancement mode MOSFET, voltage applied to the gate terminal increases the conductivity of the device. In depletion mode transistors, voltage applied at the gate reduces the conductivity. The metal in the name MOSFET is sometimes a misnomer, because the gate material can be a layer of polysilicon, polycrystalline silicon. Similarly, oxide in the name can also be a misnomer, as different dielectric materials are used with the aim of obtaining strong channels with smaller applied voltages. The MOSFET is by far the most common transistor in digital circuits, as billions may be included in a memory chip or microprocessor. Since MOSFETs can be made with either P-type or N-type semiconductors, Complementary pairs of MOS transistors can be used to make switching circuits with very low power consumption, in the form of CMOS logic. History, edit. The basic principle of the field effect transistor was first patented by Julius Edgar Lilienfeld in 1925. In 1934, inventor Oscar Hale independently patented a similar device in Europe. In the 1940s, Bell Labs scientists William Shockley, John Bardeen and Walter Hauser Brattain attempted to build a field effect device, which led to their discovery of the transistor effect. However, the structure failed to show the anticipated effects, due to the problem of surface states, traps on the semiconductor surface that hold electrons immobile. With no surface passivation, they were only able to build the BJT and thyristor transistors. In 1955, Carl Frosk and Lincoln Derrick accidentally grew a layer of silicon dioxide over the silicon wafer, for which they observed surface passivation effects. By 1957, Frosk and Derrick, using masking and predeposition, were able to manufacture silicon dioxide transistors and showed that silicon dioxide insulated, protected silicon wafers and prevented dopants from diffusing into the wafer. J.R. Legendre and W.G. Spitzer studied the mechanism of thermally grown oxides and fabricated a high-quality Si-SiO2 stack in 1960. Following this research, Mohammed Attallah and Dewan Khan proposed a silicon MOS transistor in 1959 and successfully demonstrated a working MOS device with their Bell Labs team in 1960. Their team included E. Labate and E. I. Povolonis, who fabricated the device, M.O. Thurston, Ella D'Azaro, and J.R. Legendre, who developed the diffusion processes, and H.K. Gummel and R. Lindner, who characterized the device. This was a culmination of decades of field effect research that began with Lilienfeld. The first MOS transistor at Bell Labs was about 100 times slower than contemporary bipolar transistors and was initially seen as inferior. Nevertheless, Khan pointed out several advantages of the device, notably ease of fabrication and its application in integrated circuits. Composition, edit. Usually the semiconductor of choice is silicon. Some chip manufacturers, most notably IBM and Intel, use an alloy of silicon and germanium, SiGe, in MOSFET channels. Many semiconductors with better electrical properties than silicon, such as gallium arsenide, do not form good semiconductor-to-insulator interfaces, and thus are not suitable for MOSFETs. Research continues on creating insulators with acceptable electrical characteristics on other semiconductor materials. To overcome the increase in power consumption due to gate current leakage, a high dielectric is used instead of silicon dioxide for the gate insulator, while polysilicon is replaced by metal gates, for example Intel, 2009. The gate is separated from the channel by a thin insulating layer, traditionally of silicon dioxide and later of silicon oxynitride. Some companies use a high dielectric and metal gate combination in the 45 nanometer node. When a voltage is applied between the gate and the source, the electric field generated penetrates through the oxide and creates an inversion layer or channel at the semiconductor insulator interface. The inversion layer provides a channel through which current can pass between source and drain terminals. Varying the voltage between the gate and body modulates the conductivity of this layer and thereby controls the current flow between drain and source. This is known as enhancement mode. Operation, edit. Metal oxide semiconductor structure, edit. The traditional metal oxide semiconductor, MOS, structure is obtained by growing a layer of silicon dioxide, SiO2, on top of a silicon substrate, commonly by thermal oxidation and depositing a layer of metal or polycrystalline silicon, The latter is commonly used. As silicon dioxide is a dielectric material, its structure is equivalent to a planar capacitor, with one of the electrodes replaced by a semiconductor. When a voltage is applied across a MOS structure, it modifies the distribution of charges in the semiconductor. If we consider a p-type semiconductor, with now the density of acceptors, P the density of holes, P equals now in neutral bulk, a positive voltage, Vg, from gate to body, see figure, creates a depletion layer by forcing the positively charged holes away from the gate insulator /semiconductor interface, leaving exposed a carrier-free region of immobile, negatively charged acceptor ions, see doping. If Vg is high enough, a high concentration of negative charge carriers forms in an inversion layer located in a thin layer next to the interface between the semiconductor and the insulator. Conventionally, the gate voltage at which the volume density of electrons in the inversion layer is the same as the volume density of holes in the body is called the threshold voltage. When the voltage between transistor gate and source, Vg, exceeds the threshold voltage, Vth, the difference is known as overdrive voltage. This structure with p-type body is the basis of the n-type MOSFET, which requires the addition of n-type source and drain regions. MOS capacitors and band diagrams, edit. This section does not cite any sources. Please help improve this section by adding citations to reliable sources. Unsourced material may be challenged and removed. January 2019. Learn how and when to remove this message. The MOS capacitor structure is the heart of the MOSFET. Consider a MOS capacitor where the silicon base is of p-type. If a positive voltage is applied at the gate, holes which are at the surface of the p-type substrate will be repelled by the electric field generated by the voltage applied. At first, the holes will simply be repelled and what will remain on the surface will be immobile, negative, atoms of the acceptor type, which creates a depletion region on the surface. A hole is created by an acceptor atom, for example, boron, which has one less electron than a silicon atom. Holes are not actually repelled. Being non-entities, electrons are attracted by the positive field, and fill these holes. This creates a depletion region where no charge carriers exist because the electron is now fixed onto the atom and immobile. As the voltage at the gate increases, there will be a point at which the surface above the depletion region will be converted from p-type into n-type, as electrons from the bulk area will start to get attracted by the larger electric field. This is known as inversion. The threshold voltage at which this conversion happens is one of the most important parameters in a MOSFET. In the case of a p-type MOSFET, bulk inversion happens when the intrinsic energy level at the surface becomes smaller than the Fermi level at the surface. This can be seen on a band diagram. The Fermi level defines the type of semiconductor in discussion. If the Fermi level is equal to the intrinsic level, the semiconductor is of intrinsic, or pure type. If the Fermi level lies closer to the conduction band, valence band, then the semiconductor type will be of n-type, p-type. When the gate voltage is increased in a positive sense, for the given example, this will shift the intrinsic energy level band so that it will curve downwards towards the valence band. If the Fermi level lies closer to the valence band, for p-type, there will be a point when the intrinsic level will start to cross the Fermi level, and when the voltage reaches the threshold voltage, the intrinsic level does cross the Fermi level, and that is what is known as inversion. At that point, the surface of the semiconductor is inverted from p-type into n-type. If the Fermi level lies above the intrinsic level, the semiconductor is of n-type. Therefore, at inversion, when the intrinsic level reaches and crosses the Fermi level, which lies closer to the valence band, the semiconductor type changes at the surface as dictated by the relative positions of the Fermi and intrinsic energy levels. Structure and channel formation, edit. See also, field effect, semiconductor. A MOSFET is based on the modulation of charge concentration by a Mohs capacitance between a body electrode and a gate electrode located above the body and insulated from all other device regions by a gate dielectric layer. If dielectrics other than an oxide are employed, the device may be referred to as a metal insulator semiconductor FET, MOSFET. Compared to the Mohs capacitor, the MOSFET includes two additional terminals, source and drain, each connected to individual highly doped regions that are separated by the body region. These regions can be either P or N type, but they must both be of the same type, and of opposite type to the body region. The source and drain, unlike the body, are highly doped as signified by a plus sign after the type of doping. If the MOSFET is an N-channel or NMOS-FET, then the source and drain are N and regions and the body is a P region. If the MOSFET is a P-channel or PMOS-FET, then the source and drain are P and regions and the body is a N region. The source is so named because it is the source of the charge carriers, electrons for N-channel, holes for P-channel, that flow through the channel. Similarly, the drain is where the charge carriers leave the channel. The occupancy of the energy bands in a semiconductor is set by the position of the Fermi level relative to the semiconductor energy band edges. See also, depletion region. With sufficient gate voltage, the valence band edge is driven far from the Fermi level, and holes from the body are driven away from the gate. At larger gate bias still, near the semiconductor surface the conduction band edge is brought close to the Fermi level, populating the surface with electrons in an inversion layer or N-channel at the interface between the P region and the oxide. This conducting channel extends between the source and the drain, and current is conducted through it when a voltage is applied between the two electrodes. Increasing the voltage on the gate leads to a higher electron density in the inversion layer and therefore increases the current flow between the source and drain. For gate voltages below the threshold value, the channel is lightly populated, and only a very small subthreshold leakage current can flow between the source and the drain. When a negative gate source voltage, positive source gate, is applied, it creates a P-channel at the surface of the N region, analogous to the N-channel case, but with opposite polarities of charges and voltages. When a voltage less negative than the threshold value, a negative voltage for the P-channel, is applied between gate and source, the channel disappears and only a very small subthreshold current can flow between the source and the drain. The device may comprise a silicon on-insulator device in which a buried oxide is formed below a thin semiconductor layer. If the channel region between the gate dielectric and the buried oxide region is very thin, the channel is referred to as an ultra-thin channel region with the source and drain regions formed on either side in or above the thin semiconductor layer. Other semiconductor materials may be employed. When the source and drain regions are formed above the channel in whole or in part, they are referred to as raised source forward/drain regions. Comparison of N and P-type MOSFETs. Parameter NMOSFET PMOSFET. Source forward/drain type N-type P-type. 1 channel type. 2. Mohs capacitor. N-type P-type. 1 gate. 2 type. Polysilicon N and P+. Metal M tilde conduction band M tilde valence band. Well type P type N type. Threshold voltage, VTH. 1 positive, enhancement. 2 negative, depletion. 1 negative, enhancement. 2 positive, depletion. Band bending downwards upwards. Inversion layer carriers electrons holes. Substrate type P-type N-type. Modes of operation, edit. The operation of a MOSFET can be separated into 3 different modes, depending on the voltages at the terminals. In the following discussion, a simplified algebraic model is used. Modern MOSFET characteristics are more complex than the algebraic model presented here. For an enhancement mode, N-channel MOSFET, the 3 operational modes are Q-TOF, sub-threshold, and weak inversion mode, edit. When VGS, where V sub GS is gate to source bias and V sub TH is the threshold voltage of the device. According to the basic threshold model, the transistor is turned off, and there is no conduction between drain and source. A more accurate model considers the effect of thermal energy on the Fermi-Dirac distribution of electron energies, which allow some of the more energetic electrons at the source to enter the channel and flow to the drain. This results in a sub-threshold current that is an exponential function of gate source voltage. While the current between drain and source should ideally be 0 when the transistor is being used as a turned-off switch, there is a weak inversion current, sometimes called sub-threshold leakage. In weak inversion, where the source is tied to bulk, the current varies exponentially with V sub GS, as given approximately by I sub cap D almost equals I sub cap D0 e raised to the fraction with numerator V sub GS minus V sub TH and denominator N V sub cap T power comma, where I sub cap D0 equals current at V sub GS equals V sub TH. The thermal voltage V sub cap T equals KT divided by Q. And the slope factor N is given by N equals 1 plus the fraction with numerator C sub dip and denominator C sub ox comma, with C sub dip equals capacitance of the depletion layer and C sub ox equals capacitance of the oxide layer. This equation is generally used, but is only an adequate approximation for the source tied to the bulk. For the source not tied to the bulk, the sub-threshold equation for drain current in saturation is I sub cap D almost equals I sub cap D0 e raised to the fraction with numerator V sub cap G minus V sub TH and denominator N V sub cap T power e raised to the negative fraction with numerator V sub cap S and denominator V sub cap T power period. In a long channel device, there is no drain voltage dependence of the current once V sub DS is much greater than V sub cap T. But as channel length is reduced, drain-induced barrier lowering introduces drain voltage dependence that depends in a complex way upon the device geometry, for example, the channel doping, the junction doping and so on. Frequently, threshold voltage VTH for this mode is defined as the gate voltage at which a selected value of current ID0 occurs. For example, ID0 equals 1A, which may not be the same VTH value used in the equations for the following modes. Some micropower analog circuits are designed to take advantage of sub-threshold conduction. By working in the weak inversion region, the MOSFETs in these circuits deliver the highest possible transconductance to current ratio, namely G sub M of slash I sub cap D equals 1 divided by open paren N V sub cap T close paren. Almost that of a bipolar transistor. The sub-threshold IV curve depends exponentially upon threshold voltage, introducing a strong dependence on any manufacturing variation that affects threshold voltage, for example, variations in oxide thickness, junction depth, or body doping that change the degree of drain-induced barrier lowering. The resulting sensitivity to fabrication or variations complicates optimization for leakage and performance. Triad mode or linear region, also known as the ohmic mode, edit. When VGS, VTH and VDS. The transistor is turned on, and a channel has been created which allows current between the drain and the source. The MOSFET operates like a resistor, controlled by the gate voltage relative to both the source and drain voltages. The current from drain to source is modeled as I sub cap D equals mu sub NC sub ox W over L times open paren V sub GS minus V sub TH close paren times V sub DS minus the fraction with numerator V sub DS squared and denominator 2 close paren, where mu sub N is the charge carrier effective mobility, W is the gate width, L is the gate length and C sub ox is the gate oxide capacitance per unit area. The transition from the exponential subthreshold region to the triad region is not as sharp as the equations suggest. Saturation or active mode, edit. When VGS, VTH and VDS greater than or equal to VGS VTH, the switch is turned on, and a channel has been created, which allows current between the drain and source. Since the drain voltage is higher than the source voltage, the electrons spread out, and conduction is not through a narrow channel but through a broader, 2 or 3-dimensional current distribution extending away from the interface and deeper in the substrate. The onset of this region is also known as pinch-off to indicate the lack of channel region near the drain. Although the channel does not extend the full length of the device, the electric field between the drain and the channel is very high, and conduction continues. The drain current is now weakly dependent upon drain voltage and controlled primarily by the gate source voltage, and modeled approximately as I sub cap D equals mu sub NC sub ox over 2W over L times open bracket V sub GS minus V sub TH close bracket squared times open bracket 1 plus lambda V sub DS close bracket period. The additional factor involving lambda, the channel length modulation parameter, models current dependence on drain voltage due to the early effect, or channel length modulation. According to this equation, a key design parameter, the MOSFET transconductance is G sub M equals the fraction with numerator partial differential I sub D and denominator partial differential V sub GS equals the fraction with numerator 2 I sub cap D and denominator V sub GS minus V sub TH equals the fraction with numerator 2 I sub cap D and denominator V sub of comma, where the combination VAF equals VGS VTH is called the overdrive voltage, and where VDSAT equals VGS VTH accounts for a small discontinuity in I sub cap D, which would otherwise appear at the transition between the triad and saturation regions. Another key design parameter is the MOSFET output resistance route given by R sub out equals 1 over lambda I sub cap D. Route is the inverse of GDS where G sub ds equals the fraction with numerator partial differential I sub ds and denominator partial differential V sub ds. ID is the expression in saturation region. If lambda is taken as 0, an infinite output resistance of the device results that leads to unrealistic circuit predictions, particularly in analog circuits. As the channel length becomes very short, these equations become quite inaccurate. New physical effects arise. For example, carrier transport in the active mode may become limited by velocity saturation. When velocity saturation dominates, the saturation drain current is more nearly linear than quadratic in VGS. At even shorter lengths, carriers transport with near zero scattering, known as quasi-ballistic transport. In the ballistic regime, The carriers travel at an injection velocity that may exceed the saturation velocity and approaches the Fermi velocity at high inversion charge density. In addition, drain-induced barrier lowering increases off-state QTAF current and requires an increase in threshold voltage to compensate, which in turn reduces the saturation current. Body effect, edit.